So let's start talking about mechanical work and what that actually is. Work is defined as, and notice that work is not a vector, work is defined as the dot product F dot delta R. In other words, just the magnitude F delta R cosine theta. That works for a constant force. If you have a changing force, and for this example we'll have to assume that the force is parallel to the displacement, for a changing force, you can figure out the work done by just finding the area under the curve. Notice that if the area is above the x-axis, that's going to be positive work, whereas if the area is below the x-axis, that will be negative work, and you have to add those up. Work is negative if the force is negative, or the area is below the x-axis. If you are using calculus, then the work can be calculated for any force function just by integrating. You may not have even seen this yet in your math classes. This is, of course, only required for the C kids. But really, all this means is you are finding the area under the curve. To give a geometric interpretation, what you're doing is you're multiplying the force F up here, F, times a little dx, an infinitesimal displacement, dx right there, and you're calculating that area. And then, let's go to a different color, then you're adding to that this force times this area, but times that little dx, same width of dx, and you're adding that area, and you're doing that for an infinite number of these little tiny dx's until you get the entire area under the curve. That's all that this thing means right here, is just the area under the curve that you will soon learn. So, mechanical work, notice it is a dot product. You only do work if your force is got a component parallel to your displacement. And, well, what is the evidence of work being done? Evidence of work being done is that the kinetic energy of the object changes. In fact, that gives us what is called our work-kinetic energy theorem. And that is this right here. The work-kinetic energy theorem is this. The net work done on a system will be the change of kinetic energy of that system. So, if you're doing work on something, its kinetic energy will change. And kinetic energy, what is kinetic energy? Well, it's energy of motion. So if something is in motion, it has kinetic energy. By the way, the kinetic energy does depend on the frame of reference that you are observing from. But kinetic energy is, there's the formula right there, K equals 1/2 mv squared. So what I'm going to do is I'm going to prove that the amount of work done will equal the change in this thing that we're defining as kinetic energy, which depends on the mass and depends on the speed, but it's the speed squared. Here's the proof for a force that is parallel to displacement. It can be proven for any situation, but this is the easy proof where we have a force, we got a block right there of mass m, and we're exerting a force F on it, and we're doing that through a displacement of delta x. So we're exerting this force for this whole delta x distance right there. So let's go ahead and prove that the energy gained by this thing is, in fact, 1/2 mv squared. So work is F delta x, F dot delta x, and those are both vectors dotted on each other, but that's going to just give us a scalar. So the force on this thing is just going to be its mass times its acceleration, Newton's second law, times delta x. Simple substitution right there. Next up, well, what's the acceleration going to be? Well, we know that the acceleration will be the change in velocity over time. No big surprise. And how far will it go in that time? Well, delta x, this is Merton's rule here. Well, and so this right here is the average velocity, and there's our time. So we know these two things, that the acceleration will be v final minus v initial over t, and the distance traveled, displacement, will be the average velocity times time. So let's do a substitution right here. Go to a slightly different color. So that means that the net work is force times distance, force dotted on distance, but that's going to be, here is my force, ma, times delta x, which is average speed times time. And when we multiply all that out, you just simply get this thing right here. M times v final squared minus v initial squared over 2. So here's just rewriting this thing. Let's just rewrite it to look like this. 1/2 mv final squared minus 1/2 mv initial squared, which is simply this over here, just rewritten. And that's starting to look familiar. So if we define kinetic energy as this 1/2 mv squared expression right here, then what is this up here? Well, 1/2 mv final squared must be the final kinetic energy. 1/2 mv initial squared must be initial kinetic energy. Final minus initial is going to be the change in kinetic energy. QED, we have shown that by doing work, by exerting force F on an object through displacement delta x, its kinetic energy changes by that same amount. Another way to write this is kinetic energy initial plus the net work you do is kinetic energy final. The work changes the kinetic energy. By the way, this is of course also true for a non-constant force in any direction. This will be true as long as you use dot products.